Welcome back to the second part of the lecture. So before the break, we had a discussion of some basic elements of quantum support vector machines, and we reminded ourselves about things we went through last week. And one of the more delicate aspects where there's a lot of ongoing research is the encoding of the data. So typically what we would have is some input which we would prepare. So this could be all the qubits being in a specific state, typically state 0. And then we would perform a rotation, or we could have a basis encoding, as we discussed last time. And then we would have, after the encoding part, we would then set up the processing of the specific algorithm. And that would contain a series of different gates, which then depend on the type of algorithm which we want to implement. And then finally, we have the measurement part. And these kind of algorithms are run in a hybrid way, which means that after the measurement part, which you see here, you would typically then transfer the optimized data which you have with the parameters you have, this parameters data, which could then be the parameters of both the different gates here and also the way we encode the data. And then you would optimize everything with a calculation of gradients on a classical computer. And then when you have new parameters, you would then perform again the processing part, perform the measurement, and then back and forth again till the gradients essentially vanish. So this is the way you would typically implement either a quantum support vector machine, but also a quantum neural network. And as we will see also next week, when we're going to discuss Boltzmann machines, this is actually not so different from what we end up doing in all these different machine learning methods. So the encoding part plays a very important role here. Now, what we are going to do now is essentially to go through the different slides. So we have on the whiteboard notes, we have these examples on how to encode the data. But then when we now have encoded the data, we need to think of how we compute this kernel matrix, where the similarity or inner product between quantum states is evaluated. And this quantum kernel, which is the quantum mechanical equivalent of the classical kernels, which we discussed in the previous weeks, they are in a way meant to capture complex relationships in the data. And that might be difficult for classical kernels because we have, through entanglement and the superposition, we have the possibility to access a much larger space. So the quantum gates and circuits, once the data is encoded, then a series of quantum gates, which forms a quantum circuit, is applied. And these gates manipulate the quantum states to perform the equivalent of the support vector machine's algorithms, optimization, and decision-making steps. So after the quantum operations, then we perform a measurement on the output state, and this result of this measurement provides the classification outcome, which is analogous to deciding on which side of the hyperplane a data point lies. So that means that with a given state phi of x, as we discussed before the break, then the phi of x should then correspond to a specific output y of I. So the core idea is to use what we call a feature map that encodes the classical input x into a quantum state phi of x in an exponentially large Hilbert space. So mathematically, a quantum feature map is simply a unitary circuit which acts on an n-qubit register which has been initialized to all state 0. So this is just a tensor product of all the zeros here. So that means that what we have then, if you go back to this image, this first unitary transformation is then represented by this encoding part, which you see here. And we would then represent this in terms of the state phi of x with a unitary operation. And before the break, we discussed one way of doing that by using the block sphere representation of a given qubit. So this would typically be a unitary operation which acts on a single qubit at a time. So you could think of that as we did with the VQE, we could think of that as us performing a rotation matrix and then perhaps a Hadamard operation on a single qubit. So this state depends on the input x, and the choice of ux is analogous to choosing a classical feature mapping in kernel methods. And common quantum feature maps include amplitude encoding and also angle encoding, as we discussed. So amplitude encoding is one of the techniques we discussed before the break. And then we also have the angle encoding, where rotation whose angles are functions of variable x. And once the data encoded as quantum states, you would define a quantum kernel as an overlap between states. And then a simple definition is what normally is called the fidelity here, is actually this state here. This kernel matrix K of x. So this is one of the basic steps of a quantum support vector machine. So the kernel is actually the squared amplitude of the inner product of the two quantum states. Another common version is actually this one, but measuring this amplitude directly can be difficult due to the absolute value. And many of these quantum support vector machines implementations and theoretical definitions use a squared overlap. So in any case, the kernel measures similarity. If phi of x and phi of x prime are closed in Hilbert space, then we know that this kernel is large. If they're very far apart from each other in Hilbert space, then this overlap is normally very small. So the quantum kernel is then a function that measures the similarity between the two quantum states, which are then obtained by applying a quantum feature map to classical data. So in other words, each classical vector is mapped on to a quantum state phi of x via feature map, and the kernel is defined by the inner product. So this forms a positive semi-definite kernel matrix on a data set, just as we had in the classical support vector machines. Sorry for this. So we will then have to translate the classical data point into a quantum data point. And this is normally achieved by setting up a specific circuit, which we also discussed before the break. And then we need what is called a parameterized quantum circuit that then processes the data in a way that in the end, we can apply a measurement that returns a value like -1 or +1 in case we have a type of binary output case. So a typical parameterized quantum circuit could then be us performing all these rotations. So like in the previous case, we had an example with 8 features, which we then could encode into 4 qubits, and where for each qubit, we needed 2 angles. We had a rotation around the y-axis and a rotation around the z-axis for each qubit. And then after that one, we can have a series of different operations, which are then akin to the specific type of problem which we are wanting to solve. So a parameterized quantum circuit will then have parameters corresponding to these angles, the way we would typically encode the features. And then we would have different gates which are set up in order to perform the final operations. So following that kind of ansatz, you would then have a kind of problem where you operate with this unitary transformation. You perform the rotations. This is a typical way by which you would encode the features of a given data set. And then you operate with a parameterized circuit where you have parameters phi and the parameters theta. And these kind of ansatzes are normally called quantum variational circuits, because we are actually going since and this is actually a very important aspect, since K is a quantity which defines a semi-positive definite matrix. It means that this is a quantity which always will be larger or equal to 0, and which again means that we have a lower limit. So we could actually set up a variational calculus approach where we then know exactly that we do have a minimum. And with that one, we could in a way proceed much in the same fashion as we did with a variational quantum eigensolver. So there are many similarities with the variational quantum eigensolver, also in the way we calculate the derivatives. If you remember back from the variational quantum eigensolver, when we were calculating the gradients then, we had an analytical formula where we simply needed to calculate the expression for the Hamiltonian for an angle theta plus minus pi half. And this formula, which we have for these variational circuits, is something which we will also use both for quantum neural networks, which you can think of as a kind of quantum variational neural networks, and also for the quantum support vector machines. So typically, you would only use the quantum feature map to translate the classical data into quantum states. And then you will build a kernel of the support vector machines out of these quantum states. And after you calculated the kernel matrix on a quantum computer, you would then train the quantum SVM the same way as the classical support vector machines. So basically the kernel then is simply going to be given in a traditional way by these transformations which you see here. And the idea is that we choose a quantum feature map that is not easy to simulate with a classical computer. We may actually obtain a quantum advantage. This is actually a debate, and there is no proof yet that the quantum support vector machine brings a quantum advantage. But there is an argument, if you go into this article here, is that there is for sure no advantage if we use feature maps that are easy to simulate classically, because then we would not need a quantum computer to construct a kernel. Actually, the way you encode the data, the way you perform this feature map is a big research field in quantum machine learning. So for the feature map, you end up with this ansatz which we discussed earlier, and where this product here only leads to type of interactions of CI, CJ, and non-interacting term CI. So as I said, there are many different types of feature maps, and I'm going to leave some of these slides uncommented, and I just leave it to you to actually read through some of these references here. So when we are now going to estimate these quantum kernels using a software like PennyLane, we would then use a feature which is called Q-node circuit that when encodes X, and then it encodes X prime as well via the adjoint. So a typical PennyLane recipe, you would first have the angle embedding template. So you would then define your quantum machine learning device. Wires correspond to the number of qubits. So in this case, you would have 2 qubits. And then we define this quantum machine learning quantum node, which then inherits this device. And then in this particular case, we have defined just 2 simple data sets. So this is a code which you cannot run on your in your Jupyter notebook, because it's just a skeleton which contains some of the basic ingredients. So angle embedding encodes the vector x1 into 2 qubits via rotations, and QML adjoint, which you have here. So the angle embedding does this angle transformation, which we discussed in the previous lecture. And then we have the QML adjoint here, which then applies the inverse embedding for x2. And then the output probability of measuring, let's say, the 0,0 state is exactly the square overlap of the 2 embedded states. And that defines actually your kernel matrix, the Kij. And by doing that and using a utility which is called kernels_matrix, you can then evaluate this kernel systematically. So the first thing you would need then is actually to set up. If we go back to the equations here, you would then set up this term here for a given value z, and then you have the adjoint here for the value x, and that gives you then the kernel matrix. And computationally, this is then encoded in this function which we have defined here, the circuit, where we first have the angle embedding, and then we simply do the adjoint of that one. And that gives us the kernel matrix Kij, which we are looking after. So as we said, the quantum feature map, x into phi of x, combined with this kernel k of x and x prime, and that defines the quantum support vector machine kernel. The intuition here is that the quantum device is implicitly computing a rich similarity measure via its high-dimensional state space. And this is analogous, in a sense, to the classical kernel trick, but potentially more powerful, because quantum kernels, as we mentioned, can potentially offer advantages over classical kernel methods, such as speed-up, accuracy, flexibility, and robustness. So there are tons of choices for this U of X, as we also discussed before the break. And the most common simple maps include this angle embedding or rotation, which we also looked at before the break, where we would simply have a set of rotations and where we then perform the tensor product of all these different qubits at the end. So this produces a product states. There is no entanglement in this specific case. So this maps X of I simply to an angle on the block sphere. So we are not entangling the states. So when we then encode the normalized data vector directly into the amplitudes, so if you have 2 qubits, you could actually map these states here to a linear combination of this type here. And this uses exponentially many amplitudes and can be powerful, but requires complex circuits. So let's switch back to the Jupyter notebook now and stay with that one for the rest of the lecture, because we also need to discuss some of the codes here. So we will stay now with the Jupyter notebook for the rest of the lecture, and we are going to look into many of these features, but please feel free to play around with these different programs and adapt them to your own interests or your own specific scientific cases if you're interested. So below here, we will see the examples of this applied to 2 data sets. So the typical entangling of the feature maps is actually to combine rotations with entangling gates. For instance, the CC feature map, which was used in this paper, when you can find the references down at the end of this Jupyter notebook, that would typically alternate a single qubit rotations with control Z gates between the qubits. And that creates an entangled states whose overlaps can capture correlations in the data. So in Penny Lane, the way you would do this is something like this. So you would have, for one of the specific qubits, the wires I, and then you have I plus 1, and etc. So you can then perform a rotation around the Z axis, and then you have a C naught gate where you entangle 2 qubits, and then you have a further one where you now perform a rotation on the Z axis on qubit I here. So this would be a typical examples on how you can actually make this more complicated and entangle the feature maps. So in principle, these are inspired by classical polynomial kernels, and you can encode in quadratic or higher terms. So you can, for example, apply RZ, Rx gates on each qubit, and you can also use multi-qubit rotations to create cross terms. And the choice of feature map obviously affects the kernel. So remember also that when you do a classical support vector machine, the kernel becomes like a set of functions which you can play around with as parameters. And since it's often very difficult to make a plot of the hyperplane beyond 2 or 3 dimensions, then you would typically end up playing around with different kernels. It can be a Gaussian, it can be an exponential, or it can just be a polynomial set of polynomials. So typically what you would then do once this is defined, you compute the kernel on an actual quantum hardware. And typically this involves running a quantum circuit multiple times. So we do the same thing which we did with the variational quantum eigensolvers. And then we simply estimate the final probabilities. And for the overlap kernel, you measure the probability of a certain outcome after applying these 2 operations here. So alternative schemes also include what's called a swap test, which uses an ancilla qubit to directly estimate overlaps. But this normally requires extra gates. So normally in this NISQ era for quantum computing, you would then try to avoid having 2 lengthy circuits. So in summary, the quantum kernel is given by the inner products of quantum-defined feature space. All computations on a quantum device yields kernels, which are scalars. And the heavy lifting of classification, for instance, optimizing the amplitudes, remains a classical task. And typically that's done by classical support vector machine software, where you use the quantum computed kernel matrix. And a kind of this hybrid approach leverages quantum hardware where it's needed in the kernel evaluation and classical hardware for the optimization. So you will often see that these algorithms they would then, after they've done the quantum circuit part and the quantum computation with the kernel matrix, you would then do the optimization part after the measurement on a classical computer. So if we now remember back what we had for the classical ones, when you have given some training data and you make a quantum feature map, define the kernel, then what we would end up solving is, if we're dealing with a binary case, so this can be extended to a multi-class situation, then you would typically solve the standard support vector machines using a standard linear algebra optimization. And often this is just a convex optimization problem. And these equations, irrespective of the kernel, which are then, in this case, run through a quantum computer, the equations which you see here are solved on a classical computer, but where you have a learned quantum kernel. A key point in training is that the training is still classical. You use a conventional convex solver. So we introduced 2 weeks ago the CVX-opt package, but there is also another library which is called lib support vector machines on the kernel matrix. And the quantum part is in computing Kij, and this is sometimes called a quantum kernel estimators. Alternatively, you can approximate gradients of a parameterized kernel for optimization, but we are typically dealing more with the kind of hybrid situation where we have the quantum kernel, which is set up by the quantum computer. We perform the measurement on it, but the optimization is run on a classical computer where we set up these equations here as a linear algebra library. I'm not going to go through everything here. You can read through some of them, and also several references which I put in. But if we now go look at the kind of computational complexity, the classical support vector machine has a training which roughly runs like n cubed. This is a number of floating point equations. And ns here, where we have the inference of ns, which is the typical number of support vectors. The quantum kernel estimation takes normally nq times n squared, where nq is the quantum circuit time per inner product to compute all the Kij, plus the classical n cubed operations when we are setting up the optimization part. The quantum linear support vector machine runs typically as a potential to run like log n for training under ideal assumptions. And but these things are still a little bit not fully clear, and it's an actual research area in the literature. So if we now look at the penny lane setup, we would typically, after we have installed penny lane, we would then import it. It's pretty common now to use this in connection with scikit-learn, which has the support vector machine functionality baked in here. You'd simply import it as an SVM. And then you would define a quantum device. You can define the number of qubits which you have, the number of shots you want. So here in these codes, which you will find here in the beginning, these are codes which do not run. They are simply just set up to so that you can see what you would need to bake in. And then you would define the quantum feature map. So this performs the angle embedding. And this feature map returns expectation values. Though for kernel computation, you still use a different approach. And alternatively, you can directly define a unitary as we had above here. And that returns the quantum ML state. And the Q node returns the state now. For kernel computation, you actually want to overlap two circuits as shown below here. And this is what we discussed earlier. So you have the templates angle embedding, and then you have the adjoint, and that simply returns the probability of this function squared. And if we want to measure the probability of zeros, this is actually what it would return. And so we would and set it like this and compute kernel matrices. And for training, note that these codes again will not run since the data have not been defined. We would then set up an array with data with X train and Y train. and then we would proceed with the training part. And at the end, we would apply this to our test data. And this is where we would actually test whether the model we have developed makes a good prediction or not. And then we can compare that with a classical quantum support vector machines. So in practice, what you need to consider when you're setting up the algorithms is the number of noise and shots. If you use a real hardware or finite shots, each entry is a noisy estimate that is common to run many shots, many experiments to reduce the variance, as we did with the variational quantum eigensolver. So that's why it's so handier to have studied the the variational quantum eigensolver in project number 1, because the basic recipe for the parameterized quantum circuit is something which we set up in that case as well. We would need some data pre-processing, as we discussed before the break. So the classical kernels often require normalized or scaled inputs. And this is something we would do before we actually perform the computation with the quantum kernels. So this kind of data pre-processing is something we would do with a classical computer. So there's obviously a computational cost. So if we have an n times n kernel on a quantum device, this actually requires quite many circuits. And for large n, this can be clearly very slow. So you might use just a subset of training data or some low rank approximations. So what could happen then, it would be useful to make a principal component analysis and reduce the dimensionality of the number of features so that you actually reduce the dimensionality of the kernel matrix. And this is often done in applications of quantum computing machine learning algorithms. And then we also have hyperparameters like we did with the standard support vector machines. We need to set the margin. If we want to have a soft margin, we need to specify that, etc., etc. And we will also need many of the standard machine learning methods to try to figure out which are the optimal parameters. And that means that the cross-validation scheme, which would also be run on a classical computer, would be implemented. So in Penny Lane, if we summarize, you would implement a quantum support vector machine. So Penny Lane is a pretty good library. You would choose a feature map and implement it as a Q node. You define a kernel function via this function you have defined, this Q node. You compute the kernel matrices with the quantum QML kernels, and then you train and predict using a support vector machines with the pre-computed kernels. So in the steps here, as we also discussed in the previous lecture, just to remind you of that, we would encode the data. The classical data is encoded into quantum state using a quantum feature map. We have the quantum kernel computation. Then we have the classical support vector machine training. And then we make a prediction. So the new data is classified using trained SVM with a quantum kernel. So one of the classical data set is actually the Iris data set. And here we have a plain scikit-learn implementation. This is the first part where we would use a classical support vector machine. So this you would import the SVC package, which means that it stands for support vector machine for classification. And we load the Iris data and we import the kind of measures we want to deal with. So in our case, it's the accuracy score. We can also include the F1 score, which is defined below here. And then we import the data set and we split the data into train tests. So this is the standard input and splitting the data into 75% for training and 25% for test data, which is not then included in the training. And then we import the min-max scaler, which means that we then scale the data by scaling the train data and the test data. And then when we have done that, we would then typically perform the singular value support vector machine classification. And in our case, after we've trained here, we will then make a predictions with a trained model, and we use this predict function. And then we calculate the accuracy and use other metrics So in this particular case, the accuracy is actually pretty good. It sets up the accuracy score, and it also defines the F1 score. And in this case, we actually have three features, and the precision for all of them is actually given by essentially 100%. So it's a very good fit. I just wanted to define another score, which some of you may not have encountered, which is also included in the scikit-learn as a library. So scikit-learn has lots of functionality. It's a very good library for machine learning. It does not contain advanced deep learning methods. So if you are dealing with neural networks, convolutional neural networks, autoencoders, etc., this is where you would have to use either TensorFlow or PyTorch or some other advanced libraries. So in this specific case, we have also included the F1 score, and there's a small addendum here. So the F1 score is defined as the ratio between the precision times recall and precision plus recall, where the precision is just given by the true positives divided by true positives plus false positives. And then the recall is actually true positives divided by true positives plus false negatives. And the F1 score typically ranges from 0 to 1, where 1 simply means a perfect precision and recall, while 0 means either precision or recall is actually equal to 0. And the quantum mechanical implementation of it follows very much the same procedure. So in this specific case, what we also could include, if we want to do some further pre-processing, we can import the principal component analysis in order to reduce the dimensionality of the problem. So the principal component analysis, just to remind you of that, is essentially you diagonalizing the correlation matrix and keeping the largest eigenvalues, which correspond to the largest variances. And if you do that, then you could say that those features in the correlation matrix, which have the largest eigenvalues, these are obviously in superpositions of the feature vectors. You would then keep those which have the largest eigenvalues, and hopefully, if the amplitude of these vectors is so that there is one feature which stands out, you could then simply claim that there are some central features which you can keep, and then you can discard the other ones. So here we set up again, as we discussed earlier, in this case, we will have 4 qubits to encode the information. We set up this Q node, which we discussed earlier. So this is our quantum device, and we have 4 qubits. We then do the angle embedding, and then we take the adjoint of that one, and this returns the quantum kernel. So here we have the quantum kernel. And then with the quantum kernel, we then have, and remember now that this is actually done on all calculations are done on a classical computer. If you have access to a quantum computer, you would actually run these calculations with setting up the quantum kernel on an actual quantum computer. And then we perform the same thing as before, except that now the kernel is given by this quantum kernel. And then we make the predictions. And in this specific case, we have a perfect fit again. So this is perhaps not the most impressive case which we can deal with. So there is also a Qiskit implementation, which you can look at if you want to. For the similar case, this is the same data set, and we are using scikit-learn again. We do the same kind of pre-processing as before. But then Qiskit has actually its own function for the feature map, and then it sets up the quantum instance where we have these packages here. It runs 1,024 shots. The advantage of using Qiskit is obviously that you can run this on actual quantum computers. There is a demonstration here on credit card data. So this is a way to define an output which can be bad or good credit. So we generate a small data set of financial features. In this specific case, we have the income of a given client, customer. the depth ratio, age, and so on. And then we encode them into quantum states via the angle embedding. We compute a quantum kernel, which is then our state overlap matrix, and then we train a classical support vector machine using scikit-learn. And finally, then we evaluate the accuracy, precision, and recall. If we want to add other kinds of measures, you can do that. And again, here we use this PennyLane's qubit simulator is used throughout. And hopefully the code is heavily commented, as you can see here. So the first part would just be a toy data set with 3 features. And this case is income of a given client in thousands. There's a depth ratio, which is a fraction of income. And then there is age. And then you want to predict whether this customer is going to pay credit card debt or not. So we distinguish between a good credit and a bad credits. And these are just drawn from different Gaussian clusters for illustrations here. So after generation, then we scale these features into suitable ranges, either 0, 1 or 0 to pi, before we encode them into qubits. So essentially what we did for the iris data is something which we will also do for the credit data here. And here we have a number of samples, which we just put to 50. And then these are just made up data. So just keep in mind that these are just simulated data. And then we set up the mean of the good, the covariance of the good, the mean of the bad, and the covariance of the bad. And when we've done that, we have the good data and the bad data. We stack these together. And then we clip unrealistic values and negative values of ratios larger than 1. And after we've done that, we can scale the data. So we have the depth scaled and the age scaled. So all the quantities are then being scaled. So that means that we want to scale the depth in the range 0 to 1, because this can often make the training easier. For those of you who have taken a course in machine learning, you know that this kind of pre-scaling of the data, pre-processing, is actually needed, because if we have big differences in the data sets, in the input data sets, this can often lead to a very poor training, and obviously then poor predictions of the model which we have trained. So to transform the data into domains where we don't have huge ranges for the set of data is something which is extremely useful to do. And it's almost done by default. So this will be the pre-processing part of the data. And then we do the typical split into train and test. So the training data, in this case, we're actually going to keep 80% of the data to be used in training. And then we have a test sample. So we have 80, and then we have 3 features, and the test samples, we have 20 and 3 features, and the test case is untouched by the training model. And this is where we would like to make a comparison on the quality of the fit. So we have this kind of 2 clusters with distinct means, and then these are clipped and scaled features into 0 to pi range. And this makes them suitable as rotation angles in an angle embedding circuit. And then we split the data into training and test, as we said here. So sometimes it can actually be useful to make this pre-training before. And before the break, we actually discussed the kind of pre-training and pre-processing, no, not pre-training, but pre-processing, which could be made. And then we start setting up the kernel circuit as before. So we use again this PennyLane's angle embedding. Each feature is used as an angle for a single qubit rotation. And we had an example before the break where we had 8 features, which we then could embed on 4 qubits in terms of 2 angles. And in this case here, we actually use 3 qubits, 1 per feature, and rotation on the y-axis. And our quantum kernel is then defined by the state fidelity, the overlap. So this has also, it's another name, it's called a state fidelity, between 2 encoded feature vectors. And concretely then we build a Q node that encodes 1 data point, then applies the inverse encoding of another, and measures the probability of the all 0 state. And this probability equals the squared overlap between the 2 encoded states. So in a certain sense, what you see here is nothing but what we had before. So we define a kernel circuit with the data sets X1 and X2 here. We have 3 qubits. We do the angle embedding, and then we have a rotation around the y-axis, and then we do the adjoint here with the same rotation around the y-axis, and this quantity here just returns the probabilities of measuring some specific state. And then the quantum kernel is actually set up by calling this function kernel circuit, and this is what it would return here. And then we test the kernel on 2 training samples, and this is it should be 1 when we compare vector with itself, and you can see now that this is actually as close to 1 as you can get. Then you can build the kernel, which is also called, as we mentioned 2 weeks ago, the gram matrix for the training data, which has a size of n train times n train, and between the test and train, which then has a size of n test times n train. And PennyLane actually has this functionality. It's actually not so difficult to write it yourself if you want to, but this is just called kernels and then the kernel underscore matrix. But here we just compute it directly for just clarity. So we are not using that functionality. And you can see now here that this is actually what we are setting up here with K-train and K-test here. And this gives you the shape of the training matrix, which should be 80 times 80. Then we would typically train the classical support vector machine. This is the way we would simply run it by using scikit-learn again. Actually, to write a code yourself is not that difficult. And in this specific case, we see that the accuracy again is pretty good on this synthetic data. And finally, we will then report evaluation metrics and visualize the kernel matrix and classification. And in this specific case, when we look at that one and look at the model performance, we're actually getting an accuracy which is, as we wanted it, 1.0. So the printed metrics confirms the model performance. And in this toy example, the quantum kernel produces an easily separated data representation, which leads to a perfect classification. Normally, we are not that lucky. That means that we would have to play with different quantum kernels and perhaps compare against the classical kernels as well. So one of the reasons why we mention quantum support vector machines is that there has been a lot of implementations in finance with quantum support vector machines, and they have given a pretty good result for financial tasks like credit scoring. Now, another topic which we will discuss in more detail next time, when we also discuss the quantum Boltzmann machines, is to set up a quantum neural network, which in principle is nothing but a variational quantum circuit that is a circuit with tunable parameters and which is trained using a classical optimizers. So a VQC, which is the kind of common denominator, they also call a parameterized quantum circuit, is then used as a quantum neural network. That means that data are encoded into quantum states. You have a parameterized circuit where you have parameters theta and phi, and these measurements yield outputs. And ABAS, which is a reference you will find at the end of this Jupyter notebook, show that certain quantum neural networks can actually exhibit a high effective dimension and thus capacity to generalize than comparable classical networks, which suggests a very potential for quantum advantage. So below here, you will find the typical mathematical foundation, state preparation, parameterized unitaries and measurement, and then discuss optimization and training challenges. And then we're going to go through some code examples where we've been using PennyLane. So again, we would need to prepare the state, and this is done in the same encoding way as we had before. So the encoding part, which we mentioned in connection with the quantum support vector machines, could be exactly the same as we do for a quantum neural network. And in that case, we would have a unitary transformation, which then could act on the same qubits at the time without entangling them. We could also define this to contain some additional features like a C-NOT gate, where we would entangle 2 and 2 qubits, and that would yield a more complicated quantum kernel. And this is again a unitary transformation. This is often done in terms of rotations and depends on the data set which we have. And then we have the variational circuit, where we would then set up a calculation where we calculate the gradients, and we would then have parameters theta and parameters which define these angle rotations. So this would often be built as a product of different layers. So we would then have, instead of just having one specific layer, we could now set up many, many different layers, as we would do with a classical neural network. So that means that the state, the final state would then be set up as a combination of this variational circuit acting on the unitary transformations, which then act on the initial state. So common circuit ansatz is something which is called hardware efficient circuits, where you have layers of parameterized single qubit rotations and entangling gates, which are repeated several times. And the structure of this VW can actually affect the circuit expressivity and trainability quite a lot. And then to produce a state vector, we measure one or more observables, which we label as a B of K on the final state. So again, the same thing which we did with the variational quantum eigensolver, where we ended up setting up the different Z gates in the computational basis and calculate the final expectation values, running this many, many times or performing many shots. Then we would then set up the final observables. And equivalently, this would just mean that we would set up this equation here in terms of these different transformations. And commonly, this B is actually a Pauli operator. And that could be the gate C, which acts on one qubit. In practice, you run this many shots on a quantum hardware, or you simulate this circuit classically to estimate the expectation values of B. So as a short summary, what you would have then is that a variational quantum model maps inputs to outputs via hybrid quantum classical procedure. And during training, the classical optimizer adjusts this theta by gradient descent. And then it minimizes a cost function, which would be your mean squared error, which is then defined on a specific data set. So the mapping is inherently quantum, and these models can in principle harness the high-dimensional Hilbert space for richer representations. So a typical mathematical example here, if you consider a 2-qubit circuit, a simple encoding would be a rotation along the x-axis for x1 and x2, and then you would have a variational layer, which could now be a C0 gate, and then you could have an angle θ1 and θ2 here, and then you would apply this Ry, the rotation on each qubit, and then entangle. And after applying this V theta, which is now V theta here to 0, 0, then you would measure this operator B, which is Z tensor product with I on qubit 0. And this is exactly what you did with a variational quantum eigensolver. And at the end, we would simply evaluate these types of expectation values. And then this f of x is compared to the target in a cost function for optimization. So essentially, what we are doing then is something which is pretty similar to what we did when we set up the variational quantum eigensolver. And these have a generic name, as we said, and the generic name is a parameterized quantum circuit. So the key element with this variational quantum circuit is actually a quantum circuit with trainable parameters acting on a quantum state. And it is central to the kind of near-term and hybrid quantum classical approaches which are being implemented nowadays. So the data encoding and ansatz design determine the expressivity of this variational quantum circuit. So simple encodings are typically rotations on each qubit, while more complex feature maps may exploit entanglement. So this becomes, again, a kind of play around with in order to see and to run many experiments and see which type of parameterized circuit works best. So here are some simple exercises where you can simply compute the state for just an explicitly 1-qubit variational quantum circuit, which is actually pretty simple to set up, and then find the expectation value of z as a function of x and theta. This mimics very much what you did in project 1 with a variational quantum eigensolver. So next week, when we are going to discuss the Boltzmann machines, you will encounter many of the same features which we have here. So the quantum neural networks are essentially just multi-layer variational quantum circuits, which mimic the classical neural network architectures. And you can think of each layer as adding a nonlinear quantum neuron to the network. And a simple one is just a sequence of encoding and variational layers. More structured architectures are possible, such as something which is called a quantum convolution neural networks and quantum long short-term memory networks. So in a convolution neural network, you will find that qubits are entangled in a localized pattern to mimic convolution. And for those of you who are familiar with the convolution neural networks, you also have the pooling operation. So the crucial aspect of any of these algorithms, as you also saw with the quantum support vector machines, is how classical data are embedded into a quantum state. And the most common strategies include some basic encoding. So you would map each bit of x to a qubit state, 0, 1. So this is simple, but it's normally limited to binary data. And before the break, we saw an example on how we would do that for a simple data set. The more common one is actually the angle encoding, and we use rotation gates to encode real values, which would then be done through different rotations on a given qubit. So we can also have amplitude encoding, where we embed x into amplitudes of a multi-qubit state. So this is exponentially compact, but requires complex circuits to prepare. So often the simplest case is the angle encoding. There's also data re-uploading, so re-encode input as multiple layers interspersed with trainable gates. This normally increases expressivity. So there's also a Hamiltonian encoding, which we haven't covered, but you will find references to that in the end here. So the examples here are examples which we will look a little bit more into next week as well. But here we have a variational classifier. And before we start with a discussion of Boltzmann machines, we will begin next week's lecture with a basic reminder of some of the basic features here. And then we will look at the examples which follow down here. So one thing I wanted to mention is that in the same way as we did for a variational quantum eigensolver, we would typically, when we are looking after the gradients of the function we want to optimize, we use what's called the parameter shift rule. And for many gates, like with a P as a Pauli gate, you can actually compute this gradient in terms of the expectation value for theta plus pi half minus the expectation value of theta minus pi half, as we had in the case of a standard variational quantum eigensolver. But this is something which we will pick up again next week. And I invite you to take a little look at how we implement a QNN with Penny Lane, because we will start next week's lectures with a short discussion of these examples here. And you will find again the variational quantum neural network for credit classification. But we are going to stop here now and start with a discussion of these codes and the way we implement a quantum neural network using Penny Lane. And the application which we have is an application to the credit card score, which we discussed earlier in connection with the quantum support vector machines.